Fail. Since we up and running, let me just update the title. Oh, now let's check it. Okay, Twitch has updated. Let's check YouTube. Okay, YouTube is also working. Let's get into it. So last time we were working on resizing the window, and we were stuck at the last minute. Turns out I was missing this one line of code, and that fixed the issue. It was mentioned in the comments for the previous video, but at the time I had to rush out. So yeah, but now it's all working, and yeah, can even make this full scale. Yeah, it just works. Yeah, cool. So today we'll continue to tutorial 9 and 10. And yeah, let's get
previous
into it.
tutorials, I've shown how various commands can be recorded to a command buffer.
I do keep getting this P signal semaphore thing, but just look it up. Vulkan P signal semaphore glitch error message. Okay, there's a solution. First, create a new vector of semaphores. The size must be equal to the count of images of the swap chain. Let's call this vector swap chain semaphores. In the VK present info p wait semaphores. This is a new validation, and most Vulkan tutorials got this wrong when Vulkan was young, hence many people get this validation. I'll go with solution A as it is very simple to implement. Just move the semaphore to the perch swap chain data and not the frame and flight data. Okay, this is probably something to do in the swap chain. I'll just check it out. Control F, semaphore. Okay. That's something to do with that. Control F, semaphore. What even is a semaphore? I think we'll learn this later in the tutorial, so we'll fix it then. Okay, at least I know there is some form of solution here. Okay.
For example, currently we begin the render pass, bind our simple graphics pipeline,
Let's continue with this.
push constants are a way to pass a small amount
Let me just get the source up. Then TV projector, source projector. Yeah. And let's make this small. Yeah.
Constant data to a shader via Vulkan
Yeah.
command buffer rather than writes to memory or copy commands. In previous tutorials, I've shown how various commands can be recorded to a command buffer. For example, currently we begin the which in turn binds the associated vertex buffer data. And finally, we record a command to draw the vertex buffer data before ending the render pass. We can use the vk command push constants function to update arbitrary data to our command buffer before issuing a draw call. For example, we could use it to store an object's color or an x and y offset to apply to each vertex in the vertex shader. Note that all vertices in the draw call must share the same push constant data. Additionally, it becomes really easy to draw multiple copies of the same object. In our command buffer, we first record the push constant data followed by a draw command, and simply by overwriting the push constant data with a different offset and a second draw command, we will have drawn our object twice but at two different.
Yeah, so this is basically the foundation for how we create multiple objects and do the transforms and things like that.
Positions. Push constants have one major
Interesting.
drawback, and that's their limited size. The Vulkan spec only guarantees 128 bytes of space. Some devices may provide more space, which can be checked using the max push constant size variable. Somewhat akin to how we need to provide binding and attribute descriptions to our graphics pipeline so that it knows what to expect for the format of the vertex buffer data. In the case of push constants, we need to provide push constant ranges to our pipeline layout. A push constant range is very simple and only contains 3 fields. The stage flags field specifies what.
Why do you go into like swaption stuff? I'm guessing maybe render in systems.
Shader stages will have access to this push constant range. For example, if I wanted this push constant range to be accessible only by the vertex shader, then I'd just use the vk shader stage vertex bit. The offset and size fields are the start offset and size in bytes consumed by the range. Note that the small capacity for push constants isn't per shader, so you can't get additional capacity by creating a different push constant range for each shader stage. The Vulkan spec only guarantees 128 bytes of space shared between all shader stages. So you could do something like create a range with the first 64 bytes for the vertex shader and a second range with the latter 64 bytes for the fragment shader. But unless you have a reason to specifically do so, I find it much more straightforward to use one shared push constant range for all shader stages. Okay, to use one shared push constant range for all shader stages. Okay, let's get to coding. First, I'm going to open the LVE model header and just copy these 3 lines, including the GL.
LVE model. That's CPP HP. Let's close everything else. Just open it up as required. Model. I think we'll need these 3. For now, let's get this.
Then I'll open the application implementation and paste them in near the top.
Let's do this. Libs. Libraries. Control C. Um, shift all this up. STD. Libraries and STD. This time I will not be updating CLine in the middle of stream. Save any other updates for after stream.
Now, just inside the namespace, I'll declare a new struct called simple push constant data with a GLM vector.
Okay, so struct simple push constant data GLM vector offset and then GLM vector hello vector save.
Temporary and will eventually be restructured. Next, in the create pipeline layout function, we need to provide a push constant range. So declare and initialize an empty VK push.
Yeah.
Called push constant range. Then set push constant range.stage flags to VK shader stage vertex bit. Bitwise OR operator.
Yeah. VK push constant range push constant range measures semicolon curly brackets and comma and push constant range dot stage flags equals VK shadow stage vertex bit as a fragment bit offset
Stage fragment bit. This signals that we want access to the push constant data in both the vertex and fragment shaders. Then set push constant range.size to size of simple push constant data. You could also initialize the fields directly in the braces. Just below, update the pipeline layout info to have a push constant range count of 1, and set the p push constant ranges field in the braces.
okay, what we do
Just below, update the pipeline layout info to have a push constant range count of 1, and set the p push constant ranges field to equal the address of the local.
Yeah, 1 and push constant range.
Then scroll down to the record command buffer function, and underneath the model bind function call, create a for loop with int j equal to 0.
Say record command buffer that's it.
And j plus.
Okay, it does this of for loop for and holds for plus
Create a local simple push constant data.
the only benefit to doing plus plus instead of I plus plus, I know there's like an execution difference. Let's see C plus plus for loop R plus plus versus plus plus R. And plus plus I is strictly better for iterational, simply increments the value. When not optimized, I plus plus creates a copy of I's value, increments I, then returns a copy made earlier. Of course, in an optimized build, these two would be exactly equivalent, but index loops can sometimes change to more abstract iterator loops. Okay. Interesting, did not know this. Same results, same compiled code. Okay, interesting. So in the future, just use plus plus I instead. Okay, let's go back to the video.
And initialize the push.offset field to equal 0 for the x offset, and negative.
So here, copy paste. Function 6. Let it change something. Let's okay. Yeah,
J times 0.25 for the y component. Next, set push.color equal to 0, 0, 0.2 plus 0.2 times j.
why is it giving J instead of I? Very strange. Push offset 0.5, 0.5. 0.0 and offset 0.2 minus 0.5 plus J into no need for this to be flow. Then 0, 0. 0.2 plus 0.2,
So essentially, we're going to draw a
0.2 plus 0.2 into G. Star R. I'm guessing that was just an ordering issue. Oh, okay, should be fine. Let's put some brackets just for readability purposes. Okay,
copies of our model that vary in color from dark to lighter blue. Now we need to record our push constant data to the command buffer. So call vk command push constants data with arguments command buffer at image index, pipeline layout, followed by the stage
and
flag,
this is
so
already
both the vertex and fragment bit.
generated.
0 for the offset, then size of simple push constant data, and lastly the address of the push data. Finally, move the model draw function call to inside the for loop. This way, our command buffer will now draw 4 copies.
Okay, cool.
Using slightly different push data files to expect the push data. So navigate to your vertex shader file, and just above the main function
Vertex shader file.
by push underscore constant in brackets, uniform push with a capital P, curly braces push with a lowercase p, semicolon.
And layout push constant uniform push push. Yeah.
This is add vec2 offset and vec3 color. Note that the order here must match the order spec.
Vec2 offset vec3 color.
Push constant data struct. As far as I know, the name of the uniform doesn't really matter and can be whatever you want. I usually just use the same name as my instance, starting with a capital. Also note that only one push constant block can be used per shader entry point. Anyway, next let's update the position value by adding push.offset. So within the draw call, this means that each vertex
plus push.offset plus push.color.
same amount, effectively moving the entire model. Next, we could just set frag color equal to push.color, and then we wouldn't have needed to use the VK shader stage fragment bit. But instead, I'll remove this line, as well as the line declaring the frag color output variable. Then select and copy the entire layout definition and navigate to your fragment shader file. First, remove this line declaring the frag color input variable, and then above the main function, paste the push constant layout definition. The only remaining change is to update frag color to instead be push.color. Also,
Okay, let's see.
first, remove declaring the frag color output.
Frag. Let's delete this. Copy this.
Then select and copy the entire layout definition and navigate to your fragment shader file.
I'm just going to do push. No color.
This line declaring the frag color input variable function. Line declaring the frag color output.
And deal with like this.
Then select and copy the entire layout definition and navigate to your fragment shader file. First, remove this line declaring the frag color input variable, and then above the main function, paste the push constant layout definition. The only remaining change is to update frag color to instead be push.color. Also, I'm not sure if I mentioned this in a previous video, but whatever build system you are using, I recommend setting it up so that your shader files are automatically compiled when you build the rest of your code. For example, in my makefile, I have a build step that compiles any source shader file to an SPV file. It does this by finding all .vert and .frag files within the shader's directory, and then uses pattern sub to append the .spv suffix. Then these SPV file names are provided as dependencies for the target. Whether you use Xcode, Visual Studio, or any other build system, it is possible to set up something similar, and I recommend doing so. It's really frustrating to waste a bunch of time debugging only to realize that you haven't been compiling your shaders. So I'm going to build and run my code, and you can see here that these two lines echo that my shader files have been automatically recompiled. And that's weird. The triangle is red, but I could have swore that we'd set the color to blue. To understand what is going wrong here, I need to talk about alignment requirements. Certain objects.
Okay. Let's test the build if this is enough. Okay, compiling the shadows. Okay, compiling the scripts, building the scripts. Okay, nice. Matching what was being shown. And it still works with the resizing. Oh, yeah.
Such as
Cool.
uniforms and push constants, must be laid out to meet certain requirements. Scalars of size n have a scalar alignment of n. A vec2 has to be aligned by 2n. Vec3 and vec4s must be aligned to a multiple of 4n, and so on. This is easier to understand by looking at an example. When using a float precision of 32 bits, then our scalar value n equals 4 bytes. Therefore, a vec2 must be aligned by 8 bytes, and a vec3 must be aligned by 16 bytes. By default, the struct memory in the host's code is packed together tightly. Therefore, on the host, the memory looks something like this, where there is no space between the offset and color fields. But in device memory, the push constant struct layout requires the vec3 color to be aligned to a multiple of 16 bytes. So 8 bytes of padding will be automatically inserted between offset and color. Therefore, when we send over our data, the red and green channels are being ignored, and the blue channel is being read into the push constant's red channel. And that's why the blue triangle is appearing red. Alignment mistakes can be tricky to debug, since you won't likely ever see an error message. We can fix this by using C++11's align as specifier. Just before the color decoration in the push constants data struct, add
Okay. Align as 16.
then build and run, and your triangles should now be blue, since the
Align is 16.
layout now matches the push constants memory layout in the shader. Finally, for some fun,
Let's test it out. Yeah, nice. Now it's all blue. Okay, cool.
a bit of motion. This will be easy to do because as of the last tutorial, we've started recording to a command buffer every frame. By varying the push constant data each frame, we can create animations. So back in the record command buffer function,
Okay, we're adding some motion now.
declare a variable with static int frame equal to 0.
Oh, okay, record command buffer. Yeah. Static and frame.
Equal to frame plus 1 in brackets, mod, let's
Frame equals frame plus 1. And then modulo 1000. Okay.
animation will loop every 1000 frames. Next, I'm going to change my clear color to be 0.01 to set a darker background. Next, I'm going to change my clear color to be 0.01 to
Set out. Zero. Is it like shift? Alt shift? Yeah.
color, and then update the x component of push.offset to be negative 0.5 plus frame times 0.00.
0.5.
So I'm going to build and run my code.
Plus 0.002 f into frame.
That seems a bit slow, so I'll make things quicker. But note this is just a temporary method of animations. Game loop timing is a whole topic in its own right, with trade-offs between pinning animations to the frame rate or the system's real-time clock, etc. In summary, push constants are
Okay, let's play and see if it works. Yeah, that's too fast.
and performant way to pass.
Let's keep this vacuum. Let's load it all up. Should do 0.1.
Between
Not only
but note this is just a
add it there.
I'm using to glow the negative background color. And then update the X component of push.offset to be negative 0.5 plus
Minus 0.5. Okay.
.002. So I'm going to build and run my code.
Okay, well, let's play it. Okay, nice. It's animating smoothly. And it loops back. Nice. Okay. Cool.
That seems a bit slow, so I'll make things quicker. Summary, push constants are simpler for us to implement and will typically perform better for data that updates frequently. However, besides the obvious disadvantage of being limited in size, they are not always the best way for passing data that updates on a per frame basis. This is because minimizing draw calls is also a great way to increase performance. One way to do this is by grouping models into a single vertex buffer. So for example, instead of bind model 1, draw model 1, bind model 2, draw model 2, and so on, if I put models 1, 2, and 3 all into a single vertex buffer, then I would only need one bind and one draw command to draw all three models. However, this would not be possible if using a push constant per model. Reducing 3 draw calls wouldn't affect performance, but reducing hundreds or thousands of draw calls will start to add up. Finally, one of the most common uses for push constants is to store a transformation matrix. A transformation matrix is a rectangular array of numbers that can represent a variety of transforming operations such as rotations, scaling, translations, and so on. We will cover transformation matrices in the next tutorial as we prepare for 3-dimensional rendering. So I extremely recommend watching at least the first 5 episodes of this wonderful series introducing the mathematics of linear algebra by 3 Blue, 1 Brown. Having a good geometric understanding of linear
Combination span basis
transformations is a
vectors.
requirement for understanding how 3D graphics actually works. A link to this, as well as all the other resources, are in the description below.
Let me check it out. I already know most of this. The span one, I'm not sure. You might have called it something else in school. Let's see. Okay, so 3 blue, 1 brown. Go. 3D linear transforms, metric multiplication. Eigenvectors, eigenvalues. Abstract vector spaces. Inverse matrices rank null space. Non-square matrices as transformation between dimensions. Dot products and duality, cross products. Let's check this one out.
For example, pairs of numbers and two-dimensional vectors. Now, I imagine the vector coordinates were already familiar to a lot of you, but there's another kind of interesting way to think about these coordinates, which is pretty central to linear algebra. When you have a pair of numbers that's meant to describe a vector, like 3, -2,
There's a span thing.
I want you to think about each coordinate as a scalar, meaning think about how each one stretches or squishes vectors. In the xy coordinate system, there are two very special vectors, the one pointing to the right with length 1, commonly called I hat, or the unit vector in the x direction, and the one pointing straight up with length 1, commonly called j hat, or the unit vector in the y direction. Now, think of the x coordinate of our vector as a scalar that scales I hat, stretching it by a factor
Let's speed it up.
of 3, and the y coordinate as a scalar that scales j hat, flipping it and stretching it by a factor of 2. In this sense, the vector that these coordinates describe is the sum of two scaled vectors. That's a surprisingly important concept, this idea of adding together two scaled vectors. Those two vectors, I hat and j hat, have a special name, by the way. Together, they're called the basis of a coordinate system. What this means, basically, is that when you think about coordinates as scalars, the basis vectors are what those scalars actually, scale. There's also a more technical definition, but I'll get to that later.
Okay.
By framing our coordinate system in terms of these two special basis vectors, it raises a pretty interesting and subtle point. We could have chosen different basis vectors and gotten a completely reasonable new coordinate system. For example, pick some vector pointing up and to the right, along with some other vector pointing down and to the right in some way. Take a moment to think about all the different vectors that you can get by choosing two scalars, using each one to scale one of the vectors, then adding together what you get. Which two-dimensional vectors can you reach by altering the choices of scalars? The answer is that you can reach every possible two-dimensional vector, and I think it's a good puzzle to contemplate why. A new pair of basis vectors like this still gives us a valid way to go back and forth between pairs of numbers and two-dimensional vectors, but the association is definitely different from the one that you get using the more standard basis of I hat and j hat. This is something I'll go into much more detail on later, describing the exact relationship between different coordinate systems. But for right now, I just want you to appreciate the fact that anytime we describe vectors numerically, it depends on an implicit choice of what basis vectors we're using. So anytime that you're scaling two vectors and adding them like this, it's called a linear combination of those two vectors. Where does this word linear come from? Why does this have anything to do with lines? Well, this isn't the etymology, but one way I like to think about it is that if you fix one of those scalars and let the other one change its value freely, the tip of the resulting vector draws a straight line. Now, if you let both scalars range freely and consider every possible vector that you can get, there are two things that can happen. For most pairs of vectors, you'll be able to reach every possible point in the plane. Every two-dimensional vector is within your grasp. However, in the unlucky case where your two original vectors happen to line up, the tip of the resulting vector is limited to just a single line passing through the origin. Actually, technically there's a third possibility too. Both your vectors could be 0, in which case you'd just be stuck at the origin. Here's some more terminology. The set of all possible vectors that you can reach with a linear combination of a given pair of vectors is called the span of those two vectors. So restating what we just saw in this lingo, the span of most pairs of 2D vectors is all vectors of 2D space. But when they line up, their span is all vectors whose tip sits.
Span and basis vector. Okay. Say three-dimensional.
But I only showed the specific case of transformations that take two-dimensional vectors to other two-dimensional vectors. In general, throughout the series, we'll work mainly in two dimensions, mostly because it's easier to actually see on the screen and wrap your mind around. But more importantly than that, once you get all the core ideas in two dimensions, they carry over pretty seamlessly to higher dimensions. Nevertheless, it's good to peek our heads outside of flatland now and then to, see what it means to apply these ideas in more than just those two dimensions. For example, consider a linear transformation with three-dimensional vectors as inputs and three-dimensional vectors as outputs. We can visualize this by smushing around all the points in three-dimensional space, as represented by a grid, in such a way that keeps the grid lines parallel and evenly spaced, and which fixes the origin in place. And just as with two dimensions, every point of space that we see moving around is really just a proxy for a vector who has its tip at that point, and what we're really doing is thinking about input vectors moving over to their corresponding outputs. And just as with two dimensions, one of these transformations is completely described by where the basis vectors go. But now, there are three standard basis vectors that we typically use: the unit vector in the x direction, I hat, the unit vector in the y direction, j hat, and a new guy, the unit vector in the z direction, called k hat. In fact, I think it's easier to think about these transformations by it's kind of messy. By leaving a copy of the original axes in the background, we can think about the coordinates of where each of these three basis vectors lands. Record the coordinates of these three vectors as the columns of a 3x3 matrix. This gives a matrix that completely describes the transformation using only 9 numbers. As a simple example, consider the transformation that rotates space 90 degrees around the y-axis. So that would mean that it takes I hat to the coordinates 0, 0, -1 on the z-axis. It doesn't move j hat, so it stays at the coordinates 0, 1, 0, and then k hat moves over to the x-axis at 1, 0, 0. Those three sets of coordinates become the columns of a matrix almost identical to what it was for two dimensions. Each of those coordinates can be thought of as instructions for how to scale each basis vector so that they add together to get your vector. And the important part, just like the 2D case, is that this scaling and adding process works both before your vector. Whenever you see two 3x3 matrices getting multiplied together, you should imagine first applying the transformation encoded by the right one, then applying the transformation encoded by the left one. It turns out that 3D matrix multiplication is actually pretty important for fields like computer graphics and robotics, since things like rotations in 3 dimensions can be pretty hard to describe.
And thank you for watching. Please like and subscribe.
Okay, we're done with tutorial now.
For linear transformations in 2 dimensions.
Let's save all the changes. All finish. Tutorial. Null push constants. Convert and push. Push. Why is the task bar not hidden? Task bar behaviors automatically hide. Push all the changes. All what is happening? How does Windows do this? Yes. Yeah, the bottom one is hidden. And now it's back again.
We require a
Whatever.
2x2 matrix. Each column of the matrix can be thought of as transforming where the I and J standard basis vectors go. This one concept is probably the most important thing to remember for understanding transformation matrices. I is the vector x equals 1, y equals 0, so it corresponds to the unit vector on the x-axis. A unit vector simply means the length of it is 1. The j vector is the unit vector on the y-axis, therefore it has the coordinates 0, 1. Okay, so the basic idea is that the I and j vectors get transformed to the coordinates specified by each column of the matrix, and that the entire space gets stretched and rotates with them. In this video, I'm going to focus mostly on how to apply transformations and less on understanding the underlying mathematics. We will leave all the actual computation details to the GLM library. For more detailed explanations of the mathematics involved, I've provided some great resources in the video description. So let's start by opening the fragment shader and adding to the push constant layout a new field.
Fragment shader. We didn't need this pipeline. Yeah.
Mat2 called transform.
Not to transform. Video as well, I guess.
2 is a built-in type in the GLSL language, representing a 2x2 matrix. There also exists a mat3 and mat4 type for 3x3 and 4x4 matrices respectively. Next, in the vertex shader, I will also add the mat2 transform field, and then update the GL position calculation to multiply push.transform by position. Note that order here
Push.transform star position.
Unlike typical multiplication, multiplication using matrices is not commutative. This means that push.transform times position is not equal to position times push.transform. Then in the app implementation, we need to update the simple push constant data struct to match the shader. So add a GLM mat2.
Okay, first absolute here. GLM mat2 transform.
And I'll default initialize it to the identity matrix. An identity matrix has
one dot
main diagonal and 0 everywhere else. This is typically denoted by a capital I, and any vector multiplied by the identity matrix is equal to itself. So this is just like how any number multiplied by 1 equals itself. Note that this constructor for a GLM matrix takes one number and it initializes just the main diagonal, not every entry in the matrix. Now, if you build and run, everything should be the same, but now behind the scenes, every vertex is being multiplied by that transformation. For now, though, the transform is just the identity, so it has no effect.
Let's build and run. Just double check. Yeah, nice. It's hitching in between, but like, whatever.
I'm going to create a game object header file. I'll call mine lve game object.hpp and add a header
New simplify set of how we game object shall once. Okay, let's save and let's make a corresponding source file. Be game object.
followed by your namespace. So in my case, namespace LVE, and then class LVE.
Namespace LVE plus LVE game object.
Object. Typically, a game object is anything in the game with a collection of properties and methods. For example, in Mario, your character, the warp pipe, Goomba 1 and Goomba 2, and so on would each be a game object. For the start of this series, I'll be using a very simple object model to represent game objects. Simply put, everything will be an instance of this one game object class, which will consist of each property that the engine has, regardless of whether or not that game object requires those properties to function. So for example, a Mario game object may require a property that tracks Mario's current power-up status, be it a mushroom, fire flower, tanuki suit, and so on. However, using this system, even the Goomba game object would have this property, even though it will never be used in the program. Of course, this is extremely inefficient as the game grows in complexity and more component types are created, but it's quick to implement and maintains maximum flexibility, which is great for us right now
This is
since we will
simple
often be
game
changing
object.
things and prototyping different features. I feel obligated though to at least mention some alternatives right now. An entity component system is really the way to go in my opinion, but object-oriented designs exist as well. Each have their own advantages and disadvantages. I've included 3 resources in the description below. The first explains game object models and provides an example of object-oriented design. Next is an old iOS tutorial, but it explains well the concept of entity component systems and different ways they can be implemented. And finally, this tutorial by Austin Moreland goes through his C++ implementation of an ECS. I really like this implementation, and it is very similar to what I plan to eventually implement down the line. So each game object will have a unique ID. So add a public type.
Let's send okay, he hasn't put it in the description.
Alias using ID type equal to unsigned int. Then add a private ID type member variable called ID. Now to ensure that each game object will be created.
Okay, let's public private using ID or unsigned
unique ID. We're going to make the game object constructor private. So LVE game object, ID type, object ID, and a member initialization list to initialize the ID variable with object ID. Next,
the game object. Okay, let's see, ID object ID ID object ID most quickly brackets. Another weird one to write out.
public function static LVE game object called create game object. And in its body, declare and initialize a static ID type variable called current ID equal to 0. Then return an LVE game object initialized with the current ID ++. Make sure not to
Okay, startup LV game object. Now we're like finally at the stage where it's like similar-ish to like doing 2D stuff in like Unity perhaps. Current ID, oh no. Create game object, and curly brackets, then startup ID T, current ID equals 0 term LV game object current ID ++, and here we have ID T. Okay, whatever, let's leave
increment
it.
operator here. Otherwise, all our game objects will be created with the ID 0. And then add a getter function, ID type, get ID, that simply returns the game object.
ID T, get ID, brackets return current ID ID.
I'm going to delete the copy constructor
Okay.
and assignment operator because we want to avoid having duplicate game objects. But I'm going to enable the move constructor and assignment operator to use the default.
Yeah, let's see. LV game object const LV game object and equal delete LV game object game object delete subject for what is this? Why are we
Let's start
doing
adding some
the pointer to the pointer? Yeah, good.
properties to this game object class. So include LVE
Should include LV model
.hpp as well as memory from the standard library. Then I'll add a shared pointer with an LVE
okay, std Hash include memory.
Called model, and then a GLM vector member called color. Next, I'm going to define a new struct called transform.
Okay, now it's all under public only. std shared pointer, we model GLM vec3 color. Under sources. I'll go to fit. Godless Vulkan. It's a huge pain, but it is the latest technology.
Component,
Oh,
and add a field GLM vec2 called.
well, I wouldn't recommend looking up any Vulkan tutorials. Why not? That's currently what I'm doing basically. This is the only like decent one I found, but even this, like 4 years old, so the setup is quite a headache. Like even before I got started, I had to figure out how to install everything, to figure out how CMake works, because I haven't touched C++ in like 6 years. So I had to update myself with all of that information as well. Yeah, currently this is the best one I have found. I know there are some other ones. This is the OG tutorial guide, but I prefer watching videos. Some people can do like text only. I will fall asleep 100%. Let's continue.
Translation. This will be used to move out of field
Where did he go?
vector member called color. Next, I'm going to define a new struct called transform
No color. Okay.
2D component, and add a field GLM vector.
Yeah, let's start the transform 2D component.
Called translation. This will be used to move objects up, down, left, and right.
Translation.
Also add a new function, GLM mat2, called mat2, that for now will just return a 2x2 identity matrix. Finally, let's add this transform 2D component to the game object with a new.
Let's add reason GLM vec2 translation. Copy this GLM mat2 I just returning return nice. Return GLM mat2 confirm. Yes.
Let's add this transform 2D component to the game object with a new member variable called. Finally, let's add this transform 2D component to the game object with a new member variable called transform 2D.
Oh, it's got.
navigate to your application header and include the game object header file we just created. Next,
Now should include going back here. Should like automatically sort of fluffy.
replace the
Yeah,
LVE
whatever.
model member variable with an std vector of LVE game objects called game objects. Then you can rename the load models function.
Okay. Vector of the game object. Game objects. Not
function
fucked.
to instead be called load game objects. And finally, let's add a new function, void render game objects, which takes a
Void render game objects.
command buffer parameter.
Okay, vk command buffer. Command buffer. Yeah. Command buffer.
Now in your application implementation file, start by renaming the load models function call to load game.
Okay, first cpp load models function of control function, shift function of 6. Load game objects. Okay, cool.
Constructor, and then update the function signature to the new name.
Okay.
Next, add the auto keyword before LVE model since it is no longer a member variable, and change make unique to make shared. This is
Auto make unique, make sure.
use shared pointers because it allows us to have one model instance that can be used by multiple game objects, and it will stay in memory as long as one game object is still using it. Then auto triangle is equal to LVE game object create game object.
Enter. Let me just check what is the shot. What do my buttons do for those? What are your options? Let's see. I can just remap that to Alt Enter. That'll be quite nice. Let's see. That's Alt. And this one is show actions in. Okay, let's do C-line and Rido, I guess. C-line, Alt Enter. Okay, now let's do it for C-line. Let's just do it for Rido.